And now we're recording, so I'll take it over to you, Guy.
Cool, thank you very much. I'll just check that you can see my laser pointer. Can you sort of see the cursor on the screen? Yeah.
Yes, we can.
That's great stuff. Okay, well, yeah, I just want to say a big thank you, first of all, to the organisers for the opportunity to speak to you all. This is kind of, I guess, some time that I can use to show you some of the work that we've been doing, looking at subglacial landscapes in Greenland. And in particular, I want to give a big sort of shout out to Jackie Osterman and Kirsty Tinto, who have been working on this with, as an Englishman in New York during the past couple of years at Lamont Doherty Earth Observatory. In particular, I want to sort of show you how some of these landscapes we've been looking at can give us some insights into past climate environments and ice sheets in Greenland. And this is kind of the culmination of some work that I've been looking at for the past year, 18 months. And it's sort of, certainly in 2020, it was kind of the work that was helping to keep me sane during New York lockdown life. But I guess I'll let you guys be the judge of that statement. Cool. Yeah. Okay, so I'll give you a quick primer to begin with. So not much to say here other than just to give an overview of Greenland. And Greenland here, you can see in this satellite image, is something of a misnomer. It's pretty much the only piece of land in the Northern Hemisphere which is not green. And that's because Greenland hosts the major ice sheet of the Northern Hemisphere. And in total in Greenland, we have about 3 million cubic kilometers of ice. And that's equivalent to around about 7.4 meters of sea level equivalent. And as well as accommodating this large ice sheet, Greenland hosts a permanent population of about 40,000 inhabitants. And as we kind of see ongoing and future change of this ice sheet in Greenland, that's going to have impacts and implications for not only the local population, but also communities across the globe. And as I sort of alluded to there, Greenland is changing and not necessarily for the better. We see that from the satellite altimetry records of the last 30 or so years, Greenland is consistently losing mass year on year. So in this plot here from the latest IMBY paper, basically every bar here represents the mass balance year on year for the Greenland ice sheet. And every bar below this dashed line here shows a net loss of mass for that particular year. And you can see that not only is pretty much every year losing mass, we're seeing mass kind of which is equivalent to around about 0.5 millimeter to 1 millimeter of sea level contribution per year from Greenland. And you can see in this sort of spatial map here, the reds represent areas losing mass and the blues gaining mass. You can see the reds generally far outweigh the blues in terms of both distribution and their amplitude. So that's going to contribute into that overall net mass loss. And this loss of ice mass is predicted to continue into the future and consequently contribute several centimeters to global sea level rise this century. But obviously several is quite a vague word and deliberately so. As you can see, this plot here kind of shows sea level contributions out to 2100 for Greenland. And these kind of plots you can think of as like probability density functions for a series of different basically climate relative forcing scenarios, kind of representing that uncertainty in the possible future trajectories of climate. But also each individual scenario is shown by a bell curve with a standard deviation representing the uncertainty that's inherent in the ice sheet models and the projections. And so you can see really that plausibly there's scenarios where Greenland might not lose many centimeters of ice, in sort of single figures, but also you could have scenarios where it's right up to sort of 20 plus centimeters of sea level contribution from Greenland by 2100. And so narrowing down that uncertainty is one of the kind of key aims of this field. And one way in which we can try and get at that is to look at records of the ice sheet's response to past episodes of warming. This can help increase our confidence in our projections or predictions of future change. So it's very much that kind of concept that's familiar to many people of the past being the key to the present or the key to the future. And one of the major questions that we have is, to what extent did the Greenland ice sheet respond to episodes of warming in the geological past? And some examples of those time periods that we might be interested in are times like the mid-Pliocene warm period, about 3.5 million years ago, the last time CO2 was above 400 parts per million in the atmosphere. And then also the interglacial periods of the Pleistocene through the last million-ish years, e.g. the last interglacial here shown in this figure, about 125 or so thousand years ago. And these are kind of time intervals in the past that have been identified in the most recent IPCC assessment report as important times to understanding Greenland's history if we want to better predict and understand how it might evolve in the future. And we know there are a number of different records we can try and use to go about reconstructing past ice extent or past sea level. I won't go into this in any detail here, but I'm sure these will be familiar to many of the audience. We have records like oxygen isotopes, paleo sea level markers, offshore drilling or seismic data from the continental shelves, and sediment records recovered in the ocean realm. Also onshore geological evidence as well, particularly around the unglaciated margins, and also ice sheet models, which sort of tie off those things together. But the particular record that I want to focus on here is actually the topography itself. And so subglacial landscapes or subaerial landscapes, which can tell us something about past and present ice dynamics. And in a place like Greenland, where we have a large ice sheet, I think the subglacial landscape can be thought of as doing two main things. So the first is that it exerts a control on the dynamics of the contemporary ice sheet, but also provides a record of the behavior of past ice sheets. And this is sort of nicely illustrated in landscapes which were formerly covered by ice, but are no longer. And so you can see just a few examples here, like on the macro scale, we can look at places like North America, so not too far from where I'm sat today. And we have the Great Lakes, kind of remnants of the Laurentide ice sheet, which once covered much of North America and then deglaciated following the last glacial maximum, leaving behind these lakes. And we also have something on the more meso scale, things like glacial valleys, which can tell us that we've formerly had more sort of localized glacial flow kind of coming down through here. This is in the English Lake District. And on the more the micro scale, we can look at things like striated pavement in, for example, Central Park, not too far from where I'm sat now, or kind of glacial erratic boulders as well. So these remnants of former ice flow kind of carving its way across the landscape, depositing boulders, shaping the landscape as it does so. And actually these two photos I took myself. This is like the sort of, to say that I'm only like 99% an armchair geomorphologist. This is like the 1%, my quote unquote fieldwork photos. But in the Arctic, we actually have the opposite problem. So before I was showing some examples of landscapes which are formerly covered by ice, and we want to try and understand times when the ice was more extensive. But actually in Greenland, we're particularly interested in trying to understand times when the ice sheet was less extensive. And so the problem we have there is that there is a large ice sheet in Greenland today. So much of the landscape remains heavily obscured by the presence of that ice sheet. And one of the tools we have to try and map out the landscape beneath the ice is to use airborne geophysical surveying. And this animation is kind of running through about 10 years or 12 years of NASA's Operation IceBridge mission, which kind of dramatically increased the coverage of airborne geophysical survey data in Greenland. And the particular data set that I'm interested in when looking at landscapes is the radar or airborne radar radio echo sounding data, which can basically image through the ice sheet and give you a picture of the subglacial landscape beneath. And just to kind of note that Operation IceBridge in total has acquired now more than 800,000 line kilometers of this radar data over the past kind of 11 or 12 field seasons using aircraft like this NASA P3 here. So this is like the data set which I'll primarily be using to sort of talk about the observations and results of this in this talk. We also do have other data sets collected on some of these flights, for example, airborne gravity and magnetic anomaly data, which I will also show a little bit of as well. But I wanted to show you a quick animation of radar in action, as it were. This is like an animation that I stole from the sort of NASA visualization studio. And so look, if you look at Greenland here, we're zooming in on, and you can see this little survey aircraft here kind of flying along or crisscrossing the ice sheet. And the radar, so the radio waves that it sends down effectively are used to image through the ice sheet, and they can give us a really nice picture of the internal layer structure of the ice sheet you can see here. And also they reflect back off the interface at the bottom of the ice sheet and effectively give us along a particular flight line, a kind of map of the subglacial topography. And so that's obviously useful along a sort of 1D profile to give us a picture of the subglacial landscape. But obviously what we have now is a sufficient number of lines to sort of build up more of a 3D picture of the subglacial topography of Greenland. And so in this render, I wanted to sort of show you broadly speaking, what that landscape looks like. So this is kind of Greenland visualized in a sort of 3D or kind of 3D DEM render. And I guess the main thing I want to point out about the subglacial landscape of Greenland is that I guess the two main features of interest are that, to first order, the margins of Greenland are notably high in elevation. So we have sort of high topography, particularly along the east coast and around the south. These are mountains up to 3 kilometers above sea level, but also you see that in the north and the west as well. And then the interior is generally much more low-lying and flat and smooth in character. And now part of that is because there's a big ice sheet sat there, and that ice sheet suppresses the lithosphere under isostasy. So you have effectively the center of Greenland being more isostatically depressed than the margins. But despite that, even without that sort of first order pattern of high margins and low interior persists in Greenland, kind of irrespective of the ice loading effect. That is still a real feature. And so just sort of point out that Greenland really, you can think of it as like a sort of elongated bowl, effectively, by sort of in first order character. And so for this kind of work and this talk, I want to sort of zoom in on a particular part of Greenland that we've been looking at, and that is the north and the northwest of Greenland. And the aim of this work has been to use the morphology of the subglacial landscape in this part of Greenland to infer something about the past environmental conditions of North and Northwest Greenland. And so particularly I'm sort of talking about the kind of top left kind of quadrant of Greenland in this talk. The reasons looking at this area in particular are, for example, that we find that if we look at the satellite altimetry records and also measurements of ice sheet mass balance, we find that the northwest of Greenland is experiencing rates of mass loss that are higher than in just about any other part of the ice sheet. So to sort of highlight the northwest here, you can see this, these mass balance figures through the last kind of 30, 40 years. The purple is the total kind of ice mass balance. So it's going to see that sort of negative and consistently negative. And the contributions there from surface mass balance and the red is the discharge. So sort of basically ice kind of crossing the grounding line. And you can see that that discharge component is actually producing the predominantly producing that negative signal. But you can see that purple line there, the total discharge is kind of decreased by a larger amount than just about any other sector of the ice sheet over this time interval. So it does seem to be an area that's quite sensitive to the kind of current warming trend. And also if we look at patterns of past or future deglaciation in Greenland, we might also expect to see Northwest Greenland being an area of notable mass loss. So in this paper here by Gollage et al., they've sort of modeled the future evolution of the Greenland ice sheet out to 2100 and looking at the sort of net mass balance of the different sectors. And again, you can see the north and the northwest have these sort of lower and more negative bars here of net mass balance, showing sort of larger amounts of mass loss. And the changes in thickness as well, you can see these kind of orangey red colors here, which kind of tell you that we've got a sort of reduction in ice thickness in this sector of the ice sheet. And that's also something we potentially see if we look at numerical models of deglaciation of Greenland in the past. And we see that, for example, during some of the Pleistocene deglaciations, this is a relatively kind of schematic figure of deglaciation of Greenland, but you can see the general pattern is that Greenland loses ice kind of from the north and the northwest, and it gradually sort of peels backwards onto the highlands of East Greenland. So effectively ice in the north of Greenland and the northwest being one of the places that might retreat most readily during past deglaciations and future climate warming as well. Okay, so if we kind of zoom in on the topography of the northwest of Greenland, here's now a map of bed elevation kind of zoomed in. And you can see in this color scheme, we have kind of the higher topography along the north and the northwest coasts, and then the sort of low blue topography of the interior. That means actually that that particular part of the Greenland landscape is below sea level today, primarily because of the loading effect of the ice sheet. And then you also have these kind of glacial, these troughs beneath the sort of fast flowing outlet glaciers that kind of flow into the Nares Strait or Melville Bay. You can see these deep kind of wide glacial troughs through here, beneath the Petermann Glacier, that is, and then Humboldt here. And some of these other kind of outlet glaciers sort of cross-cutting the margin of the northwest of Greenland. And I want to sort of zoom in for like the next part of this talk on a particular area of this map, kind of with the black dashed outline here. And in particular, I want to sort of show you this 3D render of this area of the map. And this, just to kind of confuse you, we're looking basically in this render, we're looking kind of from the top left corner of the box along the kind of trend of this area. In particular, this feature here, this kind of subglacial basin or area of lower elevation, you can see in the render here. And the things to sort of point out initially are that this is like an area of lower topography, and then along the inland side of the basin, as we look at it, we see this relatively sort of steep topographic escarpment leading up to this ridge of sort of higher topography, which then sort of dips inland into the interior. And you can see that also, maybe not so clear in this render, but will become more clear shortly, this kind of area of the landscape kind of cut by some what look like channels into that landscape. But I'll come back to that in a second. So yeah, generally sort of this kind of feature, possibly sort of showing a few landscape features of interest. And I want to now show you what that looks like in the radar data. So here are a couple of radar profiles, which basically cross that topographic basin. Generally, like both profiles are going from the coast on the left, moving inland to the right in both profiles. And both profiles are pretty much parallel to each other. And so the main features to point out are, as you sort of saw before, we have this lower lying topographic basin here, delineated by this red arrow here. And you can see that particularly in this profile, that basin is notably smooth in its subglacial character compared to particularly the topography on the inland side. And you can see that on the edge of that basin, we sort of rise up on this white arrow, this sort of steeper escarpment, and then a sort of high point here beneath what's the ice divide, and then what looks like a sort of flat but tilted, if that makes sense, kind of surface, which is sort of dipping toward the inlet into the interior, which sort of shows evidence of like a sort of higher frequency but sort of shorter amplitude or lower amplitude dissection, a sort of surface roughness, but also a number of deeper kind of channel or valley features, these yellow arrows here. So we have this sort of flank which is cut by kind of what look like quite sort of steeply incised V-shaped valleys. You can see some of those examples in both profiles here, which sort of in general kind of that surface contrasts with the basin in how much more rough it is compared to the basin floor. And just for kind of reference, in total, we're underneath about 2 kilometers of ice here. So about sort of 2 kilometers down beneath the top of the ice sheet. And so those radar profiles are useful for giving us a sense of some of the features we can see in the subglacial landscape. And we want to try and move that forward now and map out some of that geomorphology in 2 dimensions using a combination of the radar profiles that we have, also the digital elevation models that we can produce using those radar profiles, and also the ice surface morphology. Now, I won't go into much detail here. Effectively, this is kind of like a satellite false render, if you like, false image of the ice surface. And I just want to sort of point out that the character of the ice sheet surface, given the right glaciological conditions, can be quite useful for mapping out features which we can see in the base of the ice. And a couple of examples I just want to point out to you are, hopefully you can see in this DEM, we have like a couple of features here which look like sort of lower valley systems kind of coming through this part of the map. And you can see they correlate with these kind of areas of brighter ice surface character here. And generally we can sort of use the ice surface character to kind of map out the spatial organization of some of the features that you can observe in the radar data as well. So if I kind of like move forward, one of the things we noted before was that there were a number of those what look like valley systems within the subglacial landscape. And if we now map that out using a combination of the radar data and the DEMs we have, we can produce this valley network, the yellow lines here. You can see we have like a relatively sort of dendritic looking branching network of valleys beneath the ice sheet, which kind of really sort of end up draining from kind of toward the grid northeast and then out the top end of this plot here. And their kind of roughness and subglacial character kind of contrasts with the relative smoothness of this subglacial basin here, which is mapped out by the red outline here. And the the white dashed line being that escarpment that kind of separates the basin from the sort of uplifted or higher and tilted topographic flank on the inland side. And just to kind of point out again that the character of the ice surface comes in quite useful here. If I sort of flick back and forth, you can see generally that this part of the ice sheet is relatively devoid of surface expressions compared to certainly this sort of north and south part of the map. Generally, sort of relatively featureless area. And we find that that sort of featureless area corresponds quite nicely to the smooth topographic basin we observe beneath the ice. So essentially, smooth subglacial character correlates with relatively smooth surface character, and vice versa, the rougher areas, you can sort of see those too. So we can use those tools to build up this, this map of the subglacial, some of the subglacial geomorphology that we can observe. And I want to sort of first touch on the valley profiles. So we saw those kind of subglacial valley networks, which look like sort of like a relatively dendritic or branching pattern. And if we look at those features on a sort of slightly different scale now, so I'm actually looking slightly further away than where we just were, in sort of wider catchment of the north of Greenland. And for sort of a separate but related piece of work, we looked at we sort of mapped out the subglacial valleys in this catchment. And effectively, we found what looks like a sort of quite elongated and sort of dendritically branching valley network. And if you look at some of the cross profiles here, you can see that closer to the kind of downstream end, the coast, we have these kind of quite deeply incised subglacial valleys, about sort of 700 meters deep, and generally sort of the elevation of the valley floor is getting higher and higher as you move up the catchment inland, as you would expect, and generally the depth of incision getting lower as well. And we can also plot out the valley longitudinal profile. So that is the elevation of the valley floor as a function of upstream or downstream distance. And you can see some of the features that kind of come out are that particularly the upper part of the profile has what looks like quite a sort of concave up shape, and then sort of stepping down through a few steeper parts of the profile towards a base level, which under, or a sort of relatively low relief level at the downstream end, which under ice-free conditions correlates very closely with sea level. So it drops down to pretty much 0 meters when the effects of ice loading are taken into account. So I think we have a few features here which are pointing us towards a possible mode of formation of this valley network. So we saw kind of relatively V-shaped channel profiles. We saw a dendritic planform pattern with sort of branching valley networks. And we saw a kind of broadly concave up longitudinal profile dropping down to a base level close to modern day sea level. And we also see this kind of broadly linear increase in the width of the channel as we move downstream. So the sort of downstream end channel width here, and then moving toward the upstream end, you can broadly see there's a fair amount of scatter, but broadly there is like a linear-ish trend that runs through that. And I think those things sort of taken together are all quite indicative of a network formed by fluvial erosion. So effectively a paleo-fluvial valley network beneath this part of the Greenland ice sheet. I haven't sort of gone into much detail here, but just to note there is some scatter in the channel width. Part of that likely reflects variations in bedrock lithology. I just want to sort of point you to, there's a talk by Abigail Langston from last year in Landscapes Live that I would definitely recommend if you'd like to sort of hear more about kind of channel width in these sort of fluvial profiles and the influence of lithology there. I can't speak into too much more about that in this talk in the interest of time, but just sort of flag that is there if you'd like to sort of visit that. So I think with that kind of in mind, we can ask the question, if we have this sort of fluvial or paleo-fluvial valley network, which looks like it formed perhaps under ice-free conditions by running water, we can ask the question, well, what happens if we simulate the effect of kind of a fluvial landscape on that landscape? So effectively, if we take the ice sheet away and if we rain on the landscape, what is the hydrological network that establishes itself? And so we did that by basically using like a sort of simple flow routing algorithm where water is effectively routed to the lowest neighboring grid cell at every point in the DEM. And we find that the blue lines that result are the let's say the valley network that establishes itself, which kind of looks broadly comparable to the profile we mapped, the network we mapped out using the geomorphology before. And we also find that the basin itself, so to sort of remember that smooth area of low topography, acts as a hydrological sink. So effectively, that basin needs to fill with water before the hydrological network can kind of complete itself and drain down to the coast. So this like topographic basin, a natural accumulation point for surface standing water under this kind of hypothetical ice-free scenario. So it might be that this topographic basin would have been a place where, under ice-free conditions, effectively a paleo-lake system might have been able to establish itself. And so if we look a little bit more closely at some of the radar profiles again across that basin, a couple of points to note are that, so on the animation here, I'm kind of flicking the extent of that modeled hydrological lake onto these radar profiles. And I think one of the things I want to point out is that generally the extent of that lake corresponds quite nicely with the extent of the smooth topography beneath. So you can see a good example here where we have like these sort of nice flat smooth areas contrasting with the sort of more rough topography on the margins of the basin. And then also we see in some places suggestions of like parts where the kind of near the shoreline effectively of this lake, you have these sort of flatter and then sort of stepped parts of the landscape, which might be kind of sort of small scale features formed by effectively shoreline erosion at the margin of a sort of former paleo lake. And it's difficult from the radar data to really kind of know exactly what we're looking at here. But one observation is that if we take some of these sort of flat sort of scarp and rise kind of type features from along the margins of the lake, and we plot their elevations, we see that under the current ice sheets, their current kind of conditions beneath the ice, their elevations sort of have a bit of scatter. They kind of have a mean elevation of about 300 meters above sea level, but with a standard deviation of nearly 40 meters. But if we take the ice sheet away and we adjust the landscape for the isostatic effect of that, we find that under ice-free conditions, those kind of near shoreline features kind of map out in a much more clustered distribution with a mean of about 650 meters, but a much lower standard deviation of only 11 meters, possibly pointing to the fact that these features might have been forming at a sort of consistent elevation in the absence of ice, so to kind of adjust for that ice loading effect. So I think we have a few lines of evidence now from the sort of hydrological sink to the smooth topography, to the kind of being surrounded by these incised kind of paleo-fluvial channels, and then the sort of possible terrace of shoreline features of near constant elevation along the kind of modeled lake margin. Might just this basin could have formerly indeed hosted kind of water in the form of a paleo lake. And one other thing we can do to test that is to look at some of the other geophysical measurements that we have from these airborne surveys. So I kind of mentioned this right at the start. We also have things like gravity anomalies and gravity modeling, which we can use to understand kind of a bit more about the geology of this area. So we'll sort of flick back briefly. Effectively, this area beneath that we saw is like a relatively smooth area of topography. And it might be that if we had a paleo lake formerly occupying this basin, we would expect deposition of sedimentary material within that basin and comparatively protection of the landscape by erosion by the sort of surrounding fluvial networks. And so we can test the hypothesis that there is actually some sedimentary infill within the basin, which might kind of contribute to that smooth bed character. And if we look at the gravity anomaly over this area, effectively the black circles here are the observed gravity anomaly. And the key point really is that there is a gravity low, which corresponds with the basin. Okay. Now, part of that is because there's the topography is lower, so that contributes as well. But we tend to find that even accounting for that, we have effectively a mismatch, which we can reconcile by introducing a sedimentary infill of about 1 kilometer thickness, which gives like a gravity anomaly, this sort of pink line here, the contribution from the sedimentary infill, which allows us to match with the red line quite nicely our observed gravity anomaly. So the gravity low we observe, it's about 15 milligauss, is consistent with the presence of a low density infill of sediment of up to about 1, maybe 1.2 at the most kilometers thickness. And briefly as well, the magnetic anomalies can also give us a bit of a clue here. So I won't go into the detail of this, but essentially we can use the magnetic anomalies to try and estimate the depth to the magnetic rock. And you might expect in this sort of scenario that the sedimentary infill will be relatively non-magnetic, and then the surrounding dense kind of crystalline ice that we know characterizes Greenland would be more magnetic. And so these purple circles are effectively estimates of the depth to the magnetic source And generally what we look for is kind of clusters of those sources that kind of maybe indicate a contact between the sort of non-magnetic sediment and the more magnetic crystalline basement. And we tend to find that they do share evidence of clustering quite close to, in places, the modeled depth of that sedimentary basin. So maybe supporting this interpretation of a low density non-magnetic sedimentary infill within the basin itself. And we can also look at a few different other profiles, and the gravity anomaly modeling suggests that if we look at a few profiles crossing the basin, we consistently find evidence that there is a low density infill that kind of reconciles the low gravity anomaly. The pattern of sedimentary infill is such that at the kind of the northern end of the basin, we have relatively low thicknesses, but as we kind of move toward the center and the sort of wider part of the basin, we have higher thicknesses kind of toward that 1 kilometre maximum. And also quite encouragingly, we find that the kind of extent of the thick sedimentary succession modeled within the basin correlates quite nicely with the observed extent of the smooth subglacial topography, which is that red outline there. So generally we see that sort of the smooth topography is correlating with the low densities, indicating a sedimentary infill within the basin. So this is kind of quite encouraging kind of signs there. And one kind of thing to note as well, and I won't go into the detail of this really, is that we have a little look at the possible formation mechanism for the basin itself. Essentially, the kind of key takeaway is that we kind of say that we can look at the subglacial topography, and particularly, if you remember back, we saw a sort of tilted flank of the basin, kind of dipping toward the inland side. That's quite consistent with effectively a model where we have an extensional fault system, or it's hard to know exactly what that would look like with the resolution of the data we have, but extensional faulting, which causes substance within the basin, and then the uplift and tilting of the inland flank. And we can even sort of try and fit the sort of form of that flank to kind of constrain something about the strength or mechanical strength of the kind of crust and lithosphere there. But that's kind of generally what we're thinking that the formation mechanism of this basin might have been. And in that sense, we can kind of imagine something akin to something like the East African rifts. I want to stress that we're looking at a much smaller scale. We're not looking at a major rift valley or system here. But in East Africa, we do see these rift systems where lakes accommodate in the kind of effectively the graben. So we're kind of maybe thinking of something a bit akin to that. We have extensional faulting causing substance of this kind of area, causing infill of sedimentary material and obviously lakes above that. So I want to sort of slightly start to pivot now and take the transition from the geomorphological and geophysical observations that we've made into starting to think a bit more about paleo environment, and what can we sort of say about maybe the ice sheet or climate history of this area based on the observations that we see. And so here I've sort of summarized maybe a sort of schematic of the kind of paleo environment that we're envisaging from the observations that we've built up. So kind of this paleo-lake system, which is accumulating a sedimentary infill within the basin, the substance of which was controlled by a normal fault or normal fault system, hard to be sure from the data we have, which is kind of causing the uplift and then the inland tilting or flexure of that inland surface. And then the sort of river network or palaeo-fluvial networks surrounding that, kind of feeding into this lake, but also then draining away from on the other side of the drainage divide as well. And the kind of, I guess, follow on from that is if we are indeed seeing a kind of preserved paleo-lake basin with a sedimentary infill in this part of Northwest Greenland, that could potentially be quite a valuable source of paleoclimatic proxy data. And one example of that from the Arctic is if we sort of hop across the Arctic Ocean into the kind of high Arctic Siberia, we have there's Lake Eldjidjin here, which is actually a lake that fills an impact crater, but obviously is not covered by ice. So they've been able to recover quite extensive sedimentological records from the lake sediments here, dating back to the Pliocene, and what's provided quite a valuable record of Arctic climate as a result, from the sort of variety of sedimentological and isotopic proxies that you can derive from lake sediments. So potentially we have a site in the other side of the Arctic, Northwest Greenland, which could be a sort of similar type of site in terms of potentially the value. The challenge being, of course, there's a big ice sheet sat there, and accessing that or even confirming some of these hypotheses becomes obviously much more challenging. But then that kind of leads me on to some of the things we maybe can say about the subglacial landscape or the ice sheet history of Greenland. from the relatively limited number of sites where we have drilling of the subglacial environment. So you can see from this map here, this is sort of from a recent paper by Drew, Chris, and others. We have a number of sites in Greenland where there's been deep ice drilling that's either got very close to or accessed the bed and been able to recover a relatively small amount of material from the base of the ice sheet. And particularly the site that I'm sort of focusing in on, largely because of its proximity to the site we've been looking at, is this Camp Century ice core. So very briefly, kind of Camp Century was to be an old US military base, kind of back in the mid 20th century. And during the time this was occupied, this sort of sub-ice sediment core was acquired in the 1960s. And you can see this sort of image here. This ice core was actually, my understanding is not complete, but my understanding is that this ice core was kind of, or the sediment core rather, was kind of basically untouched for many years and was only relatively recently been reanalyzed and re-looked at. And so you can see what this material looks like with these sort of glacial, or basically diamictons recovered from the base of the ice here. And so we can kind of look at some of the results that have come out from this, and we can maybe think about how that might tie to some of the geomorphological and geophysical observations we've made. And one thing to note is that this sediment core contains diatoms, and in that glacial diamicton at the base of the Camp Century ice core. And the majority of the species recovered, you can see in this kind of picture here, are freshwater species, and they are exants, they're living, found across the Arctic. And so some of the species are known to have evolved around about 12 million years ago in the mid-Miocene, which maybe puts some sort of upper age limit on the age of that sediment. But the other point that I want to make is that from this kind of paper by Harwood, 1986, they made a note here that I've sort of highlighted that the source area of this material and the diatoms is unknown. They kind of weren't sure where it was coming from, but they know that a likely source area where lakes may have existed in the past during pre-glacial or interglacial times is the broad low elevation region east of Camp Century. And I'm not quite sure exactly what they were referring to here. I think it's not clear exactly how much of the subglacial landscape was known at this time. Likely it was only sort of very broadly understood, but it might have been referring to this sort of broader area of the interior, generally lower lying topography, contrasting with the higher regions of the margin. But it might be that actually we have a possible candidate source for those diatoms found in this ice core, which is actually significantly closer to the site than maybe they were envisaging. And that is this sort of paleo-lake, which I've sort of mapped out here. It's not clear to me exactly like how well kind of diatoms like this would survive kind of glacial or englacial or subglacial transport before getting pretty sort of crushed and messed up by kind of glacial transport. But it's just interesting to point to note that we do have these freshwater diatoms sort of preserved in this ice core or this sediment core beneath the ice. And it may be that they are some way tied to the presence of this paleo-lake basin here. And some other things that have been kind of coming out from this sediment record more recently. This is kind of this cool figure in this paper by Chris et al., where they kind of say that we have like these sort of terrestrial material like twigs, moss, leaves, all these different kind of terrestrial kind of recovered biological materials, kind of maybe hinting back to a time when Greenland was more warm and could support vegetation of this nature. And they also look at some of the luminescence dating on this sediment, which suggests that there might have been at least one ice-free event since or at MIS 11, about 400,000 years ago. So it could be that during the last million years of the Pleistocene, there was at least one or more time when this area was free of ice, which might open up the possibility that the neighboring Paleo-lake basin and the sediments within that could also perhaps record or preserve some of those features. So hopefully I've not done too sort of bad a job of kind of butchering the kind of interpretations of this study, but I just want to point out that Drew gave a talk in Landscapes Live last year, which I would definitely encourage you to go and watch if you want to learn more about this beyond what I can sort of try and briefly tell you there. And then it sort of like leads on to other questions about, well, kind of maybe what did the sort of patterns of deglaciation of the Greenland ice sheet maybe look like? And what can our observations do to sort of support that, or I guess tell us about kind of these ideas of how extensive was Greenland deglaciation in the past and at what times did it occur? And obviously I don't have any of the answers to these questions yet because we've not sort of been able to look beyond the geophysical data. But one thing to point out is that there are a number of different simulations of the Greenland ice sheet at, for example, the last interglacial, so marine isotope stage 5E, about 123,000 years ago here. And it's just one particular simulation. It's the same simulation that was in that IPCC report figure, kind of right back at the start of the talk. And it sort of basically the point is that depending on the ice extent, the Paleo-lake basin may have become exposed during, for example, the last interglacial, or may have been earlier interglacial phases. And you can sort of see in this particular render, or we have like a tantalizing prospect where the lake basin sort of just emerges from just outside the margin of the ice sheet here, just one particular scenario. So really the point I want to make is that understanding the history of deposition and also erosion of the material in this basin as ice has kind of come and gone across this landscape could potentially be very valuable. And we may have a site where we can try and the records within that basin might be quite valuable in sort of answering some of these questions, which are challenging to answer kind of given the presence of the ice sheet in the way. So that's pretty much coming to the end of what I wanted to talk about. There are a couple of final slides, just the main takeaways. So the kind of key points that I'm sort of making here are that from the geomorphology and the geophysics, we kind of have this, what we've interpreted as an ancient or preserved paleo-lake basin and river channels preserved beneath the ice in the north and northwest of Greenland. Just for reference, the maximum capacity of that basin is about 7,000 square kilometers or 580 cubic kilometers. Just for kind of give you a broad sense of scale, that's about a third the size of Lake Erie, although I realize that there might be not as many North American audience here, but it would, if it was part of the North American Great Lakes, it would be small, but it would be not kind of completely dwarfed by them. So it's a sort of smallish mini version of, let's say, the North American Great Lakes. And it might be that the basin could contain potentially valuable sedimentary archives of, e.g., ice sheet extent or environmental conditions during some past climate intervals where maybe the Greenland ice sheet was more restricted than it is today. And as a result, that site could be potentially a promising target for the future acquisition of, e.g., ground-based seismic surveying and or sub-ice drilling. So ultimately, we could sort of imagine like a scaling up from seismic surveys, which might give us more locally a better understanding of the structure of the sedimentary infill beneath the basin than the radar data can give us. They could also tell us things about the sort of seismic velocity and the bulk density of the sedimentary material, which could tell us something about their like general character, so kind of how soft they are, or if they're more compacted, how sort of strongly lithified they are, and the sort of general structure within the basin. And that then could inform, possibly moving forward, the kind of future recovery of either sort of a shallow sediment core, or perhaps if sort of things were promising, a more deep continuous record of subglacial material within that basin. So that's pretty much brings me to the end. So I'll leave with kind of a few kind of the main conclusions I want to just re-emphasize. Effectively, we have pre-glacial, or what look like pre-glacial landscape features, e.g. river networks and lakes that are well preserved in the north and northwest of Greenland. So that tells us something about the erosional history of the Greenland ice sheet, and maybe that it's not been able to fully overprint some of these inherited features, which could tell us something about its longevity, its erosional history, and the basal thermal and ice sheet regime as well. It also tells us that during ice-free times, that Greenland was sufficiently warm and wet to support a large-scale river and lake kind of networks, and that the sedimentary deposits that are associated with those landforms and systems, if we were able to sort of sample them in the future, could potentially help us to try and constrain the timing of some of the ice-free intervals that have characterized, or that have likely characterized, Greenland's history over the past several 100,000 or even millions of years. So that is where I want to leave it. But I just want to say thank you very much for staying with me. And if you have any questions, I'm very happy to take them now. So I'll stop talking. Thank you.
Thanks, Dan. That was super interesting. So everyone, the chat is now open for questions. So feel free to write, or if you would like to unmute yourself, we can do that and you can ask the question directly. We already have one in, so I'll save my question. So we have one from Edmund Leah, who says, thanks for the talk. Does the geophysical data leave open the possibility of there being liquid water in the basin in the modern day, or is the ice simply not thick enough to be melting at the base?
Thank you very much. That's a very good question. I would like to kind of briefly whiz back, if I can. Yeah, maybe to this figure. So I think, so we do have inventories of subglacial lakes in Greenland and Antarctica, and as it stands, there is no mapped subglacial active, like existing subglacial lake within this basin. I think generally speaking, that's probably a fair assessment. It does look like the sort of signs from the basal thermal regime and the ice sheet internal layers. I think in recent models of the basal thermal state of Greenland, this area looks very much like it is frozen at the bed, and it's kind of also given the setting, if I sort of go back a bit further. Where are we? Yeah. So here, basically, this on this figure, I forgot to mention that this black line here is the modern ice divide. So the basin is actually located very close to an ice divide. So we're looking at the very low velocities and likely frozen ice at the base. So I think it's pretty unlikely that there is any kind of major like water present on, at the present day. There are one or two profiles where you do see quite kind of notably flat and smooth parts of the bed. And like, so whether that's kind of, you maybe would expect some more, like in the radar, you might expect some more bright signals of which would reflect subglacial water. So I think it's probably unlikely there is much, but I think it's not necessarily possible to exclude the possibility that there could be some either distributed water or into the sort of the realm of more like wet sediment, the sort of on that continuum of kind of water to liquefied sediment. But I think generally speaking, there's not much to suggest there is any meaningful amount of water in there today. Yeah.
Great. So I had a question. I haven't really thought about Greenland much, but what information do we have on faulting in Greenland? Because I know that faults can control, the direction of fjords and things like that. And you were talking about fault controlled basins. Do we have data on faulting beneath the ice sheet?
Yeah, that's also a good question. And I think the answer I can give you is that generally speaking, in Greenland, we see generally very, very low seismicity. There's really not any real active seismicity today. Part of that sort of likely because of the presence of a big ice sheet kind of influencing the stress regime, which makes failure on a fault underneath the big ice sheet less likely than in an ice-free world. And I don't think there's really anything, given the sort of limited observations we have, it's not particularly obvious that there's any evidence that suggests this is like an active fault system today. But I think it is a good question as to, not only this fault, there are a few places where maybe around the margins where faults have been mapped, but they're generally quite old features. And the question would be like, if it is a sort of fault controlled basin, how old might that be, and what sort of time did that tectonic activity come from? We thought a little bit about this. So one thing I can add is that we have in the Melville Bay offshore here, there's like this is like an extensional regime, if you imagine sort of separation of Canada from Greenland. And we have the Melville Bay Graben in here, which is like a sort of very clearly mapped in the seismic data extensional system. We have kind of sedimentary infill within this, like a graben here with a sort of bounding fault, which sort of trends approximately parallel to that margin, that coastline there, just a little bit offshore. And the trend of those systems is quite consistent with the trend of the kind of escarpment along the basin that we're mapping inland. So whether there's kind of any possibility that those sort of systems are somehow linked, this is kind of back to the, let's say, the kind of Paleocene, like the early part of the Cenozoic. We're looking at Eocene, Oligocene kind of type age tectonics there. So whether there is a link between those, I think from what we have, it's pretty difficult to say for sure. I think one thing that seismic data collected from the Ice Service might be able to tell us is something a bit more about the internal structure of that basin and getting it below just the bed interface, but also looking into the sedimentary structure a bit more. And that might be able to tell us something a bit more about the tectonic history or regime. Yeah.
Cool. And because I know on the map you had the higher topography in the southeast.
Yeah.
Do you know why that is? Why there's more topography there? It seems to be quite persistent.
Yeah. So this is like a good question, and there is like a debate that's ongoing about why the sort of passive margins of East and South Greenland are as high as they are. And when that sort of relates to, for example, the incision of the fjords that kind of cut that landscape, and then the isostatic response to the unloading of that material, which can kind of cause additional uplift of these mountains. There's also kind of the possibility of dynamic support by the mantle plume beneath Iceland, whether that's kind of current support or recent support from the sort of dynamic, the dynamic topography of the Iceland plume. And generally speaking as well, it sort of mirrors some of the high topography that you see on the Scandinavian side of the North Atlantic as well. And to what extent is that those sort of high mountains, are they like a remnant of the old Caledonides, the sort of the ancient mountain systems of the North Atlantic, or are they a more recently uplifted feature? And I think that's something that's still like there's still like ongoing kind of work on kind of trying to untangle that question. Yeah.
Great, thank you. Okay, I'll let Aditi read you the next question in the chat.
Yeah, so there's a comment from Neil. He says, it's interesting to note that Stephen Livingstone's 2013 predictions of subglacial lake locations in Greenland in the cryosphere hints at possible small water bodies in that basin in the past.
Okay. Yes, I think I am familiar with that paper, and I think my understanding is that sort of paper is like a prediction of kind of former or current places where water might be accommodated. I can sort of only add that is interesting, and I think that would be like something that we haven't really looked at closely enough is maybe we could use some of the ice surface altimetry data to try and see if we see any like changes in the ice surface elevation through time, which might be telling us something about any movement of water within the basin. It's not something we've really looked into. I can only sort of go back and like reiterate the point about from the geophysical data we have, there doesn't really seem to be any clear evidence for the presence of water in there today. But I certainly think there's not enough to sort of preclude that from what I've seen. But I think it is an interesting observation. But I don't have much more to add, unfortunately. Yeah.
Okay, and so we have a question from Ian Evans. This actually links nicely to a question that I had about being able to differentiate or identify potentially the processes that you sort of said that you can see these fluvial landscapes. And I'm just wondering whether you could comment on potentially how the deglaciation of Greenland's ice sheets have potentially been the reason for this, and so that sort of links into what Ian is asking. So he says, if the basin was easily deglaciated perhaps 123,000 years ago, it could indeed produce interesting paleoclimatic record, but we're more interested to know just how small the ice sheet may have been in the Quaternary. So should we just drill elsewhere? So I suppose two questions there, a bit from me and then a bit from Ian.
Yeah, thank you. So I think that I'll try and sort of broadly answer those questions as best I can. So there's a point about kind of the process behind the formation of some of these valleys. And let me move forwards. So I think one thing I can maybe add a bit more to on this is and maybe to like the extent that some of these landforms could have been modified by glacial processes as well, is that I think it certainly would not surprise me, or I certainly wouldn't rule out the possibility that some of these landforms could have been modified by glacial erosion during either sort of times of more restricted ice, times when ice was retreating or moving across the landscape. For example, in the long profile, you do see a couple of places where the profile drops down into an over deepening, essentially along the profile. And I think there's particularly one place here kind of correlates to this part here, so profile C, where I think there is evidence that you might have had kind of at one time convergent glacial flow kind of being sort of focused through like a narrow kind of existing channel, and maybe kind of cause some localized over deepening within this part of the profile. And actually, if you sort of take the profile further toward the coast, you really do see it drops down, well below sea level as you kind of get beneath the active Petermann Glacier today. And there's also kind of the hypothesis that's out there. You might have seen this paper by Benjamin Kiesling and others that have looked at the possibility that glacial outburst floods could have eroded or shaped in some way some of these valley networks. And again, I would just say that I absolutely, there's no reason to suggest that that's not the case, what we're seeing. I think the main point that I want to make is that we do sort of propose that these features are, at least to begin with, were palaeo-fluvial features, but I think there's definite evidence to suggest that some parts of those profiles have been modified more recently by the action of glaciers or kind of glacial meltwater in some form. But specifically untangling that is, I think, another interesting question that we've kind of only dipped so far into. So the second part of the question was about the
sorry, it was about the paleoclimate. Yeah, sorry.
No, so it was like basically the question was like we could look elsewhere. Yeah, so I guess there's, in some ways there's, there will be no bad place to drill, in the sense that like we have such a limited understanding of what is down there that the kind of other places that could be drilled potentially could also be very valuable. I guess what the geophysics and the geomorphology we can try and use that is to sort of maybe identify certain sites, maybe such as this one, where the records might indeed exist. But I definitely would also add that there are, there's other ongoing work, which is looking at maybe some drilling closer to the margin, which might try and look at more recent glacial history and deglaciation. And indeed, there's like, it kind of depends a bit on maybe what the question is that you want to ask. I know that Benjamin Keesing, I'm sort of throwing him under the bus again. He normally sits like right next to me, so I can't like refer to him. But he would sort of probably add that he's doing some modeling work where he's looking at kind of if you had certain sites which did or did not become ice free at certain times, what did that mean the Greenland Ice Sheet had to have looked like? So in other words, like to get ice free conditions at a particular site, what's the kind of parameter or like space within which the Greenland Ice Sheet might have looked like? Like, is there a sort of region of like ice space we can sort of narrow down the Greenland, like the extent of the Greenland Ice Sheet at those particular times? And then he sort of finds from that there are, the result of that is that there are certain sites that then become more useful because they can like constrain the extent of the ice sheet better than other sites. So you could definitely use work like that to try and narrow down as well places where you might want to sample in the future. Yeah, that's kind of probably all I would add on that. Yeah, thank you.
Great. Okay, so we have our next question from Drew Christ. It says, fantastic talk, amazing what you have found hiding beneath the ice surface. Can the geophysical data differentiate between different types of sediment in the basin? For example, between till and lacustrine sediment, or could the basin contain sediment deposited both in the lake and by glacial advances?
Yeah, that's a really great question. Thank you. Nice to hear that you're there, Drew. So I guess my answer to that would be the radar itself is a bit limiting in terms of what it can tell us. The radars, you can't really resolve much at all about the actual material. You can say the ice bed interface is, at elevation X, but beyond that, it's pretty hard to say anything more about, what happens below that. And so I think my answer would be that from the radar, or certainly the sort of maybe the more regional scale radar alone, it's pretty difficult to say anything too much about that. But I think this is where my kind of point about the possibility for seismic surveying in the future would come in, and that could maybe give us a bit more of a sense of, for example, if you could constrain things like the bulk density or the seismic velocity, in total, essentially the permeability of the material, that could give you a handle on, how soft or deformable the sediment is, maybe compared to how, or like if it's quite lithified, strongly compacted, you would sort of basically be plotting in different parts of this kind of density velocity space. I think it's perfectly plausible and probably even likely that there'll be more than one like type of sediment, quote unquote, in there. You might easily expect to see maybe a more sort of superficial till layer, and then further down you might get into the better preserved lacustrine sediment. But really that's something that from the radar data that we currently have is pretty difficult to say much about, but certainly a really interesting question. And yeah, maybe in the future that's something we can try and learn something more about. Yeah.
Okay, there's another question by Andre. He says, thank you for your talk. Is the bedrock isostatically adjusted in your analysis? And is it possible that part of the time the lake existed under an ice sheet like Lake Vostok in Antarctica?
Yeah, so the answer to the first part of the question is that yes. So in all our analysis, if I just sort of scroll back, yeah, for example, like here, we've basically isostatically adjusted the landscape for the modern ice sheet load. So basically we just sort of took the modern ice sheet away and we adjusted the landscape elevation accordingly. So all our elevations we've been mapping are under ice-free, kind of isostatically corrected conditions. So yeah, thank you very much. That's definitely an important clarification to make. The second part was about, could this have existed beneath an ice sheet in the past? I think the answer is possibly. It would obviously depend on the particular glacial conditions at the time. You would require to be basal ice sheet conditions which enabled liquid water to exist at the base. And also you would need a kind of configuration of the ice such that the basin maintained its ability to kind of withhold water. You know, if the ice sheet was configured in such a way where there was a sufficient hydro potential gradient that the water could effectively just drain out to the coast, you might not expect a lake to exist. So you'd have to be kind of thinking a bit more carefully about what did the configuration of the ice sheet look like, and what did that mean for the routing of subglacial water beneath, and also the basal thermal state in terms of the kind of whether the ice sheet was likely to be frozen at its base or liquid at its base. And in the past, when the ice sheet looked different to today, it's entirely possible that those conditions could have been favorable to that. And that's going to be something that could be looked at with like a kind of combine like a glaciological model into these things to try and see maybe what are the kind of possible configurations where you could get a lake existing under there at times in the past. Yeah, like Lake Bostock, for example. Yeah.
Great. Okay, so then we have another question from Luca Malatesta. He says, great talk, thank you. He found the correlation between ice sheet surface features and basal topography quite fascinating. And he says, are there other sites on Earth or other planetary bodies where such surface features can enlighten us about the hidden tectonics or topography?
Great question. So let me just go back. Yeah, so the answer is yes, absolutely. With a caveat that it does seem to depend a little bit on the particular glaciological conditions. In general, in places where you have, for example, quite fast flowing or heavily deformed ice, it starts to become much more difficult to kind of correlate basal features to the ice surface. An example of that is sort of down here, like where you have fast flowing ice close to the coast, where it's all a bit of it's very noisy and it's pretty hard to kind of correlate individual features. But certainly in many places in the interior, this technique can be used, and is kind of has been used in the past and is being currently used as like work is ongoing. We're trying to look at more of these features across the whole of the island of Greenland to try and kind of map out some of these like linear features in more detail. And it does seem that these features can relate to both kind of topographic features like subglacial valleys and maybe also some of the tectonic features as well. For example, it looks like in parts of East Greenland beneath the ice, there are quite sort of linear surface features in the ice surface, which might be telling us something about an inherited like tectonic structure beneath the ice. And some of this work has also been done in Antarctica as well. There's kind of a number of studies which have looked at using the ice surface morphology to kind of fill in the gaps, which is particularly valuable in regions where radar data is perhaps quite sparse. And so you can use these kind of features to sort of map out I can't speak as much to other bodies of the solar system, which I think was the last part of the question. You certainly see, for example, in some of the moons, I think like Europa, and I think one of the Saturn moons as well. You do see kind of these like ice moons. We have a lot of sort of ice surface features going on, but I think in those cases it's more often the case that they are like that's ice that's sort of not necessarily floating. It's not floating on land in the same way that we're looking at. We might be sort of looking at liquid water beneath. It's obviously I'm not an expert there, but and also they might be sort of telling us about kind of larger scale planetary deformation processes as well. But yeah, certainly these features are things that we can use in a number of these kind of ice sheet settings to better understand what's going on at the bottom of the ice, which is very valuable in areas where we have limited, for example, radar or geophysical data to do that for us. So, yeah, but thank you. That's a great question.
So there's a question by Gilliam. Thanks for your talk. Any chance there's a link between the nearby putative impact crater and this Paleo Basin, or just coincidence to find the two so close together?
Yeah, that's another great question. So do I have the right figure? Yes. So for those of you who aren't aware, there's a putative impact crater, which has been mapped very close to the margin here of the ice sheet. You can probably just about see it in this render, that sort of circular feature there near the Hiawatha Glacier. And there's also putatively a second impact crater kind of somewhere unhelpfully beneath my label in this figure. And there's like, it may or may not be that those two impact craters are linked. It is interesting that we have another kind of feature of note, potentially quite close to those two impact craters. I don't really have a sense for whether they could be related. I mean, purely from looking at the sort of the work I've been doing, there's nothing to suggest that there really is any sort of sign that an impact crater could be like genetically related to this feature. But it is interesting that they do appear together, and whether that's sort of telling us something about the ability of this part of Greenland to kind of preserve some of these features beneath the ice sheet. I think something that's interesting as well. And there are actually kind of one of the other possible, let's say, values of the material within this basin might be that depending on the relative timing of basin being active and these putative impact craters forming, depending on the sort of whole range of like other kind of criteria, it could be that sediment might even contain some other sort of record of ejecta from those impacts. But I guess we're then getting quite into the sort of speculation realm. But it's interesting to sort of think about whether there could be, record of those putative impact events preserved in any part of this area. And it might be that this basin is one place that could exist. But yeah, no, it's certainly an interesting one why we have these sort of different features in quite close proximity. There's also this kind of, and I sort of alluded to it as well, we have this like what's called the sort of palaeo-fluvial mega canyon as well, kind of through here. So there's like, does seem like quite a sort of interesting place where like a lot of these different kind of cool things going on. But yeah, maybe it's just coincidence, I'm not sure. Yeah.
Okay, we still have a couple more questions. We're working you hard today.
Yeah.
So, the next one is from Emily Bamber. She says, do you have any idea how long it would take to isostatically adjust the landscape? Just wondering if this could be used to suggest how long the area was ice-free, since it seems shoreline indicators only match up when it's adjusted.
Yeah, thank you. That's a great question as well. So this would depend on the rate at which the isostatic rebound occurs would depend on the viscosity of the mantle beneath Greenland. This part of Greenland is probably relatively high viscosity, well, relatively high compared to the east, close to the Iceland plume. But with the timescales we're looking at are probably, from my understanding of the sort of glacial isostatic, sort of modeling work that's been done, we're probably looking at timescales on the order of like several tens of thousands of years, maybe towards like 100,000 years. It's probably, very broadly speaking, the time scale you would need to kind of re-equilibrate following the deglaciation. So yes, it might well be that if we could get a handle on how long that time scale took, how long that adjustment took, that could then give us some indication of how long you would need the basin to be free in order to kind of get those paleo shoreline features at a consistent elevation. Yeah, it's not something we've looked at explicitly, but I think that's kind of one that we could look at by sort of coupling a sort of ice sheet simulation to a isostatic adjustment simulation and try and see if we could sort of say something about that. Yeah, that's a great question. Thank you.
Okay, so that's I think one of the last questions by Matthew. It's like, given a fluvial system along the center axis of the continent, are there any deviations from the typical geomorphology of river systems? For example, over deepening, which might constrain total glacial erosion?
Mm-hmm. Thank you. Let me try and go forwards. So in some ways it is quite a, yeah, so I hope to go back. It is quite an unusual drainage system in the sense that it's kind of basically running along the axis of the middle of the continent and then sort of escaping through the north of Greenland. And it kind of harkens back a bit to what I was mentioning earlier about the sort of slightly weird topography of Greenland. We have like obviously a ring of mountains surrounding the outside and then a sort of relatively lower interior. So this sort of interior drainage pattern. So what I can add to that a little bit is that we do see in the longitudinal profile a couple of places where the profile appears to be over deepened, potentially telling us something about past glacial erosion that's kind of come along and modified that river profile or palaeo-fluvial profile. We also see in a couple of places there's a couple of steps in the profile. So like, for example, about at 900 kilometers, there's like a step down here, and then another one at sort of 400 to 500 kilometers, it sort of steps down relatively steeply there. So these are kind of like what look a bit like nick zones or areas of steeper channel gradients. And we've also done a little bit of work trying to understand trying to model that using a sort of stream power type fluvial incision model to see what that sort of shape of that profile could tell us about the evolution, like its evolution. And it might be that we have a couple of episodes there of changes in base level that have caused kind of down cutting of the channel profile and resulting in those nick zones. And we sort of tried to look a bit at, can we constrain the sort of timing and magnitude of those events? And it might be that kind of for the sort of standard erosion rates, we're sort of looking at these kind of features having formed kind of, let's say, several million years over sort of the course of several million years, maybe like back into the Miocene, the Neogene, the Miocene kind of Pliocene sort of time. But it still leaves the open question of what did the landscape look like at that point, and how recently were these East Greenland mountains uplifted, and whether there's kind of been rerouting of that channel network through time. There's some interesting questions there, and I could go on for a while, but I feel like I probably should stop. But that's really interesting, and yeah, I'd be happy to chat with. If anyone's interested in chatting about that more, I'd be very happy to sort of get in touch, because that is an interesting question. Yeah.
Yeah, I mean, just a quick question I think probably that's the last question. But I just had a quick question about the luminescence dating that you just showed. That was an age of 400,000.
Yeah.
What was that age on?
Yes. So this is like not a study that I worked on, so I don't want to kind of like speak out of turn. But so I think my understanding is that this kind of was basically this material that was acquired from this subice sediment core, is it this sort of glacial or diamicton type kind of material. If Drew is here, he's very welcome to like jump on.
Oh yeah.
I think that oh yeah, she is there. Hi Drew.
Yeah, I'm here.
Feel free to jump in if you want to answer that. Yeah.
Great talk.
Cheers.
Yeah, I don't want to steal any of Guy's time to talk about his work, but those luminescent states are on an interior portion of sediment from that upper sample 1059-4. So it's feldspar grains and infrared luminescence dating on multiple grains from 2 different grain sizes. We're working on that paper right now. So hopefully I will be able to get it out to my collaborators and get that submitted eventually. So.
Oh, okay, yeah. No, thank you.
Thanks so much.
Yeah.
Brilliant. Okay, well, I think there's been a really great talk, and you have a lot of praise and thanks in the chat. So I will send you that chat, and you can have all the questions.
Yeah, thank you.
The history. But yeah, otherwise, thank you everyone for coming. Thank you, Guy, for a really interesting talk. And yeah, brilliant. Thank you very much. We can close it.
Thanks for having me. Thank you.
Amazing.